Good morning, class. We are looking at exam 2 review, chapter 3, differentiation rules. Here's exam 2 from 3.1 to 3.8, and this is part 4, section 3.6, derivatives of the logarithmic functions. All right, so 3.6, derivatives of the logarithmic functions. Y equals ln x. We want to take the derivative, and to do so, we're going to go to the exponential format, e to the power of y equals x, because we know how to differentiate exponential functions. So we're going to differentiate this implicitly, the derivative of the left side, any exponential, the answer is itself. So e to the power of y times y prime, and x is 1. So y prime would be 1 divided by e to the power of y, which is x. So simply put, y equals ln x. The derivative would be just to flip over the argument 1 over x. And if we expand that, first of all, the reason we put an absolute value because x must be positive. You remember the domain for the natural log, or basically basic log functions is from 0 to infinity. 0 is not included. So if we have ln of g of x, it's 1 over g of x times g prime. This is by the chain rule. If we call it u, where u is a function of x, 1 over u du dx, and of course u is positive, that's how we arrive at the answer. Now, reminding you of logarithmic properties to help us with this topic. So if b is positive and b is not equal to 1, y equals log x base b is equivalent to x equals b to the power of y. As we look at this one, we notice that the base is the same for both formats, and so is the exponent. So if you look at this one and go with the arrow, log x base b of equals y, that means b to the power of y must be x. And if we follow that, then for the case that is the general case, y equals log x base b is the same as b to the power of y equals x, it creates the following properties. Log 1 base b is 0, log b base b is 1, log base b of b to the power of x is x, b to the power of log x base b equals x, log x y base b is log x plus log y. Both of them have the same base, known as the product rule. Log base b of x over y is log x base b minus log y base b, known as the quotient rule. Log base b of x to the power of n is n log x base b. N sits in front. That is known as the power rule, some of which are easily seen here just by the arrow. Okay. And some of them we have proved before in algebra, so we should have no problem with that. Now, what happens when we go to specific cases? For example, in the case of a common log, the base is 10. So log x base, then we don't write it as such. We just write it as log x, which means 10 to the power of y is x. And these properties, you should be able to see how we can go from the general case for a specific case where the base is 10. In this case, we are dealing with the common log. Bear in mind, for example, number 2 says when the base b and the argument b, this is the argument, are the same, the answer is 1. So when you don't write the base is 10, so the argument must be the same, therefore 10, and the rest of them follow in the same manner. Now, if we go to natural log, where we write y equals ln x, so log x base e, we never write it in that format. Rather, we write it as ln x, which means the base is e. So y equals ln x means e to the power of y must be x, and it gives rise to the following properties. For example, ln 1 is 0, and the rest of it. As far as the graph is concerned, exponential functions, logarithmic functions, are inverse functions. So y equals e to the power of x, y equals ln x. They are inverse functions. Therefore, they are symmetric with respect to the line y equals x. And this is the change of base formula. Log x base b is log x over log b with any base, for example, base a. However, we go with a common log or a natural log for the sake of calculation, and you're putting it into a calculator to work out for us. As far as this is concerned, this point has coordinates 1, 0, and of course, this would be 0, 1. So for the logarithmic function, for example, y equals ln x, ln x is negative. That means below the x-axis between 0 and 1. It's 0 at 1, and it's larger than 0. That means positive above the x-axis when x is larger than. As far as differentiation is concerned, ddx of ln x is 1 over x. ddx of ln of g of x is 1 over g of x. 1 over g of x times g prime of x. So that's the synopsis of the properties that will help us with differentiation as far as logarithmic differentiation is concerned. So let's take a look at a couple of examples. For example, y equals ln of sine theta. We want to differentiate that. And the dx of ln of g of x is 1 over g of x times g prime. So simply put, flip this over, 1 over sine theta. And then by the chain rule, the derivative of sine, which is cosine theta. And as you know, cosine over sine is cotangent theta. That is the final answer. Y equals e to the power of x over 1 minus e to the power of x. That requires the quotient rule. So we would write the quotient rule from the memory, and we're going to follow that. Y prime is f prime g minus g prime f over g squared. So y prime is f prime, the derivative of the top is itself, times g, the bottom, 1 minus e to the power of x, minus g prime, minus, and inside the parentheses we put, this is 0, minus e to the power of x, and then times f, which is e to the power of x itself, divided by g squared. Put this in a parenthesis and square. So what we are looking at is f prime g minus g prime f. All we have to do, simplify the bottom, and we are done. So distribute, you get e to the power of x. Distribute, you get minus e to the power of x times e to the power of x is e to the power of 2x, minus minus plus e to the power of 2x. These two cancel each other. So the numerator is simply e to the power of x. The denominator remains unchanged. So y prime is e to the power of x, parenthesis over parenthesis 1 minus e to the power of x squared. You don't have to square that. This is done. Okay. All right, let's do this. There are two ways to do this, and I'm going to do both. This is simple enough, it really makes no difference. So if we want to just, let me erase my work first. So if we want to stick with that, flip it over, 1 over x cubed, times its derivative, g prime of x, 3x squared. And the final answer is 3 over x. Now, This is simple enough that you can do it this way, it's fine. However, the more complicated the natural log, the easier the second way. And that means put the 3 in front. This is the second method. And so you're differentiating y equals 3 times ln x, and ln x is 1 over x, so 3 times 1 over x, which is 3 over x. Makes not much of a difference in this case, but it does if this gets complicated. Okay, and I can't emphasize this enough. Y equals log base 3 of square root of x. Well, we know how to deal with logs when it's a natural log when the base is e, but we don't know how to deal with it when the base is not. So what do? Simply put, we are going to go with log x base b and use the change of base formula, write it ln x over ln b. Bear in mind, you're dividing ln x by a number. That number happened to be ln b. So we are going to rewrite this as 1 over ln b times ln x. Bear in mind, what is 1 over ln b? Some number, a coefficient of ln x, 2, 5, 1, 1.8, some number. So if I want to differentiate this remains as a coefficient, and this becomes 1 over x. So y prime is 1 over x ln b. So I'm going to do the same thing here. However, before I do that, I'm going to change this to x to the power 1/2. I'm going to use number 7 here. I put different numbers so we can refer back to it, known as the power rule. And I'm going to put the 1/2 in front of the log. And now I'm going to differentiate this. First, I have number 1/2. So y prime equals 1/2. Then anytime you have a log, flip over the argument 1 over x. Then I look at the base. If the base is e, we are done. Because it's not 1 over ln b, 1 over ln 3, this is by logarithmic properties. So one more time, 1/2, the number was there. Log gives you 1 over x. Because the base is not e, 1 over ln 3, put them together, 1 over 2x ln 3. F of x is log base 5 of x squared plus 1. And I hope you realize basically we follow the same thing, but we add the chain rule to that. So if you're dealing with log base b of f of x, you have to flip this over 1 over f of x. You have to multiply by f prime by the chain rule. Then you look at the base. Since the base is not e, 1 over ln b, those are the 3 steps. Now you can put them together in the following manner. So having said that, first we're going to differentiate this f prime of x is flip this over 1 over x squared plus 1. 1 over f of x, call this f of x. Now, by the chain rule, we need the derivative of the parentheses, which is simply 2x. Then we go to the base, since the base is not e, 1 over ln 5. Now put them all together. 2x over x squared plus 1 ln 5. It's inside the parentheses. To make sure we understand it's the product of these two pieces. Y equals ln of 5x over x squared plus 5. Well, we can differentiate this by flipping this over, and then we need to tag along the derivative of that by the chain rule, right? Which means you use the quotient rule. Instead, we are going to go with the easy way out by breaking this into pieces. This first uses the quotient rule, ln of the top. Let me just do it in 2 steps. Ln of the top minus ln of the bottom. And now I'm going to use number 5 and write ln 5 plus ln x. This is completely broken down. Okay, let me. So ln of 5x over x squared plus 5 is ln 5 plus ln x minus ln of x squared plus 5. And it's completely ready for the next step. So you want to use your logarithmic properties to decompose it completely. It makes it easier to deal with if you go that route. All right. Now let's do one by one. This is 0, y prime equals ln 5 is a number, the answer is 0, ln x is 1 over x. So ln 5 gives you 0, ln x gives you 1 over x. Minus 1 over x squared plus 5 times its derivative, which is 2x, and we are done with calculus. We are going to put them together using our algebraic techniques to finish the job. So we are going to put these two together, the common denominator of x times x squared plus 5. This would be 1 times x squared plus 5. This would be minus 1 times x. My apologies, minus 2x. Minus 2x times x. So let's see what we get here. We get x squared plus 5 minus 2x squared. We can combine these two into minus x squared. So the final answer would be minus x squared plus 5 over x times x squared plus 5. All right, so that's pretty straightforward, everybody. A quick recap. Completely decompose the log. It makes it very easy to differentiate piece by piece. All right. G of x is log of 9 minus x cubed to the power of 4. And the best course of action is to use number 7. Let me erase the work here. Number 7, the power rule, put the 4 in front. It's completely decomposed. To differentiate, G prime is, of course, write the 4. Flip this over, 1 over 9 minus x cubed. Remember, we can't decompose it any further. Then we need the derivative of 9 minus x cubed. We are looking at this one, okay, 1 over f of x times f prime of x. The derivative of 9 minus x cubed is negative 3x squared. And you look at the base. The base is missing. That means the base is 10. 1 over ln b, 1 over ln 10. Now we put them all together. So 4 and negative 3, negative 12x squared and the product of these two pieces in the denominator. So y prime is negative 2x squared over 9 minus x cubed ln 10. Y equals 1 half ln of 1 plus x over 1 minus x, and we want to differentiate this again. You definitely want to simplify the log by decomposing it completely. It makes it a lot easier. Otherwise, you have to flip this over and then use the quotient rule on that. Instead, 1 half remains outside. Ln of 1 plus x over 1 minus x. We use the quotient rule and we write ln of the top minus ln of the bottom. Now we're going to differentiate this y prime equals, we keep the number in front 1 half and then work on these pieces. So ln of 1 over x, flip it over 1 over 1 over 1 plus x, and then times g prime. The derivative of the parentheses happen to be 1, but write it times 1 minus, flip this over 1 over 1 minus x times the derivative of the parentheses this time is negative 1. So if you didn't write it here, would be okay, but now it wouldn't be okay. So times negative 1. And believe it or not, this is it. This is the end of calculus. Now we're going to do algebraic steps. So let me put an asterisk. I want to really emphasize this. One step of calculus class. This was algebra, okay? Logarithmic properties, and we're going to do a few more steps. So first and foremost, we're going to take this and change it to plus 1 over 1 minus x. I want to make sure we understand that. So 1 half remains outside. What's inside? The product of 1 plus x and 1 minus x would be our common denominator. So 1 half remains. The product of these two is the common denominator. So 1 times 1 minus x, and then the plus 1 times 1 plus x. I'm just showing you how to find the LCD and combine fractions and simplify as follows now. This is 1 minus x plus 1 plus x. Clearly, it's just true, right? Because minus x and x cancel each other. 1 half and 2 cancel each other. The numerator is 1 and the denominator is 1 minus x squared. So y prime is 1 over 1 minus x squared. As the final answer, we are done. ln of ln of 5x. And if it helps, you can literally change this. So let's say f of x, whatever. So according to this, 1 over g of x or f of x. Flip this over, 1 over ln of 5x, and then g prime of x or f prime of x. Now, just write the derivative of ln of 5x. So what is the derivative of ln of 5x? 1 over 5x times its derivative 5. I hope you can see what happened here. So one more time. Flip this over, and then take the derivative of this. Ln of 5x itself is the argument of ln, okay? So 1 over 5x times 5. This 5 cancels out this 5. So the numerator is simply 1, and the denominator is ln of 5x times x. We put the x in front. The final answer is y prime equals 1 over x ln of 5x. We want to find the equation of a tangent line for the function y equals x squared ln x at 1, comma 0. We need two things. We need a pair, which is given x, comma y, and we need the slope. To do so, we have to differentiate and plug in. To differentiate, we notice we are multiplying x squared by ln x. We put a raised dot, and we say it's f times g. We're going to use the product rule on that. So f prime g plus g prime. If f prime is 2x times g ln x, and g prime ln x is simply 1 over x, 1 over x times f, which is x. So in other words, we are looking at f prime g plus g prime f. And so the first one is 2x ln x, and the second piece, becomes just simplifies to x. Now, if I plug in, that means if I replace the x with 1, that becomes the slope. M is y prime of 1. So 2 times 1 times ln 1 plus 1. And as you know, ln 1 is 0, so the answer is 1. Now, y minus y1 equals m times x minus x of 1. Bear in mind, it's important to notice this is not the y-intercept. Okay, y-intercept would be like 0, 1. So y minus 0 equals m, which is 1, x minus 1. And so y equals x minus 1 is the equation of a tangent line in this case. Want to differentiate y equals log base 3 of 1 plus theta ln 3. A couple of different ways of approaching it. Let's just approach it the way it is. Number one, you're going to ask yourself, can I decompose? Can I simplify this log? The answer is no. So to differentiate, I don't want to say y prime. I can, but the reason I don't want to say it because this is theta is the independent variable. So I want to write dy d theta instead of y prime. You can write y prime, but dy d theta. So you're going to flip this over. Okay, flip it over. Then you are going to differentiate this with respect to theta. You're here. So what is the derivative? This is 0. Theta times ln 3 is a number. It's like 2 times theta. The answer is 2. So the answer is ln 3. And then 1 over ln b. Because is the base E? Is E? No. Because the base is not E. Okay. 1 over ln 3. Clearly, is to cancel each other, and we are done. Y prime is 1 over 1 plus theta ln 3. Just to remind you, also recognize the original function y equals log base 3 of 1 plus theta ln 3 as ln of 1 plus theta over ln 3 over ln 3. This is by the change of base formula. So you can change the base to E, so this becomes ln and divided by ln 3. This is using the change of base formula, everybody. Either way. What about y equals ln of 2 e to the power minus t sine t? I highly recommend you decompose it, and it makes it very easy. Otherwise, it's really involved if you want to differentiate this. So here's what we do. ln of 2, we are going to go with log x, y is log x plus log y. All of them have the same base, in this case, p. ln of 2 plus ln of e to the power minus t plus ln of sine t. So cut it into 3 pieces first. Decompose the log completely. And I want to go over this and reminding you that if ln of e to the power of x is x, ln of e to the power minus t must be minus t. So replace this with minus t. And now we are going to differentiate this piece by piece, starting with the first one. ln2 is a number, or ln5, or e, or 10, or 1/3. The answer is 0. This one, negative t, gives you negative 1. Now, ln of sine t, flip this over, 1 over sine t, and then times the derivative of that cosine t. So this is 0, this is negative 1. Cosine over sine is cotangent. Therefore, y prime is negative 1 plus cotangent. Pretty straightforward, everybody. So the key is when you deal with logs, know how to simplify and decompose in order to speed up the process. Y equals t log base 3 of e to the power of sine t ln 3. We are going to work with logarithmic properties first to simplify as much as possible. What do we notice as the argument? Just right here is the argument of log. E to the power of sine t ln 3. That should tell you something. E and ln 3 should tell you something. Reminding you that ln of e to the power of x is x. E to the power of ln x is x. And log base b of b to the power of x is x. So having said that, this part, we are going to put the ln 3 first and then sine t. Just look at this part. I hope you realize we haven't really changed anything. But what is e ln to the power of ln 3? E to the power of ln x is x. This, we will replace it with 3. Log of b to the power of x when the base is b is x. So look at this one. Log of 3 log base 3 of 3 to the power of sine t. Because these two are the same, this entire thing becomes simply sine t. So we have t times sine t. You can write log 3 base 3 and change it to 1, or just notice is t sine t. In other words, I would go from here to here, but if you need this step, so be it. In other words, put the x in front and then this is 1. That's what I did. Just an extra step. You don't need that. You can go right here. And now I'm going to say this is f times g, and I'm going to use the product rule on that. F prime g plus g prime f. So because again, the independent variable is still, let's say, dy dt instead of y prime. The derivative of t is 1 times, so f prime g, 1 times sine t, and the derivative of sine is cosine times t plus cosine t times t. And I'm going to put the t in front because it's awkward. Otherwise, y prime is sine t plus t cosine t. I hope you see that. If you don't simplify it using logarithmic properties, it becomes very difficult to deal with. Logarithmic differentiation. We have y equals x to the power of 3/4 squared of x squared plus 1 over 3x plus 2 to the power of 5. And logarithmic differentiation is used when the expression is involved. So what is logarithmic differentiation? Number one, take natural log of both sides. So let's take natural log of both sides. So if I take the natural log, the left side becomes ln y. What happens to the right side? We can cut it into pieces. Ln of the top minus ln of the bottom. Ln of the top is ln of this piece plus ln of this piece, and then minus ln of this piece. So the left side is simply ln y. The right side, ln of x to the power of 3/4 plus ln of square root of x squared plus 1. And remember, x squared plus 1 to the power of 1/2 or square root is the same thing. And the bottom takes a negative sign, minus ln of 3x plus 2 to the power of 5. So take natural log of both sides and, of course, simplify, decompose completely. So we're going to work on the right side. The left side is ln y. This is 3/4 ln x. This is 1/2 ln of x squared plus 1 minus 5 ln of 3x plus 2. So ln y is 3/4 ln x plus 1/2 ln of x squared plus 1 minus 5 ln of 3x plus 2. So decompose it completely. That's the first thing. Step 2, differentiate implicitly with respect to x. In this case, I should say with respect to the independent variable. Happen to be x in this case, okay? It could be t. So starting with the left side, I hope you see that it's, if you want to differentiate ln y, it's 1 over y times y prime or dy dx. So the left side is 1 over y dy dx. What about this one? 3/4 remains. ln x is 1 over x. Plus 1/2 remains. Flip this over. 1 over x squared plus 1. And then by the chain rule times the derivative of the parentheses, which is 2x. We're talking about this one, okay? Finally, minus 5 doesn't change. Flip this over. You're taking the derivative of a natural log. Flip this over 1 over 3x plus 2. And then by the chain rule, the derivative of 3x plus 2, which is 3. Now solve for dy dx. To solve for dy dx, first of all, you take 1 over y to the other side. That means the right side times y. So y times the right side. What is the right side? 3 over, so y times 3 over 4x plus this 1/2 cancels out the x, the 2, and x goes at top. And this is negative 15. So One more time. dy dx is 1 over y goes to the other side, becomes y, right? You multiply both sides by y. This is 3 over 4x. This one half cancels out the 2x over x squared plus 1. And this is minus 5, 1, 3. The product is minus 15 over 3x plus 2. You don't have to combine them because normally it takes quite some time. Just you must replace the y. Replace the y with the, let me just erase my work so you can see it. Replace the y with the original y, x to the power of 3 4 squared of x squared plus 1 over 3x plus 2 to the power of 5, and just write this, and you're done. And I hope you see how difficult it is to differentiate it if we do not use logarithmic differentiation. Now, another way that logarithmic differentiation is used when the base and the exponent are both functions of x, none of them is a number. That's one way to do logarithmic differentiation, although there is a second method. I'm going to discuss that in a moment. But for now, we are going to go with the first step. That means take the natural log of both sides. So I'm going to take ln of the left, ln of the right. And the right side pass, when I take the natural log of x to the power of sine x, it uses the power rule and sine x sits in front. Now, the next step is to differentiate. And to differentiate, we have to differentiate implicitly. This is, of course, ln y, just like before, 1 over y times y prime. The right side, we use the product rule on that, f times g. So sine becomes cosine times g. So f prime g, which is ln x, plus g prime ln x becomes 1 over x times f, which is sine x. And this is the extent of differentiation. And again, this was algebra. We continue with algebra. And at this point, we are going to solve for dy dx or y prime. Sometimes we call it dy dx, sometimes y prime. And so y prime is the right side times y. So you take this to the other side, that means multiply by it. Y times cosine x ln x plus 1 over x sine x. And now you must replace the y with x to the power of sine x, and you're done. Now, again, when the base and the exponent are both functions of any independent variable, for example, x, one methodology is logarithmic differentiation. The second method is to remember e to the power of ln x is x. So since e to the power of ln x is x, and in this case y is x to the power of sine x, we can replace the x with e to the power of ln x and say it's e to the power of ln x times sine x. This we know how to differentiate. Because remember, how do you differentiate e to any power? The answer is itself and then times the derivative of the exponent. Remember that? That's how you do exponential. So we know how to deal with the exponentials. We can go that route, or we use logarithmic differentiation. Now, what about inverse trigonometric functions? The derivative of sine inverse is 1 over square root of 1 minus x squared. The derivative of tan inverse 1 over 1 plus x squared. Secant inverse 1 over x squared of x squared minus 1. The rest of them are the negative of those. In other words, cosine inverse is the same thing, make it negative. The derivative of cotangent inverse, the same thing, make it negative. The derivative of cosecant inverse, the same thing, make it negative. So reminding you of a couple of things, sine inverse of x equals y, that by definition means sine y equals x. and y is between negative power 2 and power 2. As you recall, none of the trigonometric function is one-to-one unless you restrict the domain because all of them are periodic. So sine inverse of sine x is x. This x belongs to sine x must be between negative power 2 and power 2. Sine of sine inverse of x is x. This x belongs to sine inverse, and it's for the range of sine, negative 1 to 1. Same thing with the cosine inverse. I'm reminding you of that. And that is the synopsis of what you see. Now, instead of sine inverse of x, if we happen to have sine inverse of u, then you change the x to u, but 1 is du dx. And the reason why this is 1 is the derivative of x. So you put du dx and the rest of it. Or, for example, tan inverse of g of x, you put g prime of x. All right, the derivative of inverse trigonometric functions are given, and sine inverse equals y, sine y equals x. That's what it means. And sine inverse is the derivative of sine inverse is 1 over square root of 1 minus x squared. That's what we have. And what we want to do is to look at the proof here as an example. So let sine inverse of x be y. Okay, we want to prove this. Okay. Let sine inverse of x be y. By definition of an inverse function, sine y must be x. And we are going to differentiate this expression, everybody. We're going to differentiate this. So to do so, sine, the answer is cosine, but this is like g of x, so times g prime of x, or times dy dx, and x is 1. So we are differentiating implicitly. Sine becomes cosine times this derivative dy dx, or y prime, and the derivative of x is 1, which makes dy dx is 1 over cosine y. So the question is, what is cosine y? Reminding everybody of Pythagorean identity, sine squared plus cosine squared is 1. So if sine y is x, cosine must be square root of 1 minus sine squared y. And by the way, remember, we are talking about the fourth and the first quadrant where cosine is positive, because otherwise this is plus minus, and we take the plus. So if that is the case, square root of 1 minus sine y to the second power, that means 1 minus x squared under the radical. And so we are going to replace this with that, 1 over cosine y. That means 1 over square root of 1 minus x squared. And we just proved the derivative of sine inverse of x is 1 over 1 minus x squared. So the derivative of sine inverse is 1 over square root of 1 minus x squared. We proved that. Let's go with another one. Let's go with tangent. When tan inverse of x equals y, by definition means tan y equals x. And as you recall, the limitation we put is the same as the limitation for the sine, except doesn't have the endpoints. And so we want to prove that the derivative of tan inverse is 1 over 1 plus x squared. We want to prove that. So we want to go from here to here. Okay, so from here to here. And so we are going to use this one and do the implicit differentiation on this one. So I want to differentiate this implicitly. The derivative of tangent, as you recall, is secant squared. So secant squared y, and then y prime or dy dx, and x becomes 1. So dy dx is 1 over secant squared y. And we know Pythagorean identity. Another one is, okay, this was sine squared plus cosine squared equals 1. Also 1 plus tan squared is secant squared. So we know this as well. And so 1 plus tan squared, that means 1 plus x squared is secant squared. So we are going to replace the secant squared with 1 plus x squared. Therefore, we prove the derivative of tan inverse is 1 over 1 plus x squared. So we can see that. I hope everybody's fine with that. Now, differentiate y equals e to the power of 10x, tan inverse of x, and I'm going to put a raised dot and say this is f times g, and it requires the product rule. All right, so y prime is f prime g plus g prime f, which means y prime is e to the power of 10x times 10. That's f prime times tan inverse. Plus g prime. Now, tan inverse is 1 over 1 plus x squared times f e to the power of tan x. This is it. We're done with calculus. We are going to rewrite things. This is 10 e to the power of 10x tan inverse. This is e to the power of tan x over 1 plus x squared. And you can leave it like that. You can take the e to the power of tan x out. Doesn't help much, but basically we are done. Y equals cosecant inverse of e to the power of x. Now, cosecant inverse of x is negative 1 over x squared of x squared minus 1. And bear in mind that if you happen to have cosecant inverse of a function, then the numerator, instead of minus 1, becomes minus du dx, or minus, if you call this f of x, f prime of x, or g of x, g prime of x. So you can go with that and say d dx of cosecant inverse of g of x is negative 1 over, instead of x, now we're going to change it to u or g of x. Square root of u squared minus 1 becomes g of x quantity squared minus 1 and 10 times g prime of x. So with that being the case, dy dx is negative 1 over what goes in here. Instead of x, it goes e to the power of x. Over here, e to the power of x. And then the derivative. So according to this, we put g of x. And let's call this actually g of x so everybody can see. Call this u or g of x. So put the function u or g of x here and here. And then now we need g prime. The derivative is also e to the power of x. So clearly, these two cancel each other. So we get negative 1 over the square root of this one is e to the power of 2x minus 1. Okay, so dy dx is negative 1 over the square root of e to the power of 2x minus 1. Our last question, y equals x sine inverse of 3x, and we are going to do the same thing again. We're going to put a raised dot here, meaning you're looking at f g. We need the product rule. So y prime is 1 times sine inverse of 3x. Now plus g prime, sine inverse of 3x. Remember, sine inverse is 1 over square root of 1 minus x squared. If it's sine inverse of u, is the u dx over the square root of 1 minus u squared. So let's write it in this fashion and say, okay, what do I need here? I need the u, and let u or g of x. Let's call this one u. And so you need 3x here, and then you need the derivative of 3x here. So you need 3x here and 3 here. And this times f times x. And we are done. We are going to simplify. So a quick recap, f prime g plus g prime, the derivative of sine inverse of 3x. 1 becomes 3 because the derivative of 3x is 3, and then square root of 1 minus x squared becomes 3x quantity squared. And so this is sine inverse of 3x. This is 3x, and this is square root of 1 minus 9x squared. Y equals x cosine inverse x minus square root of 1 minus x squared. So we change this to 1 minus x squared to the power of 1/2, and we put a raised dot here. So this is f, this is g, requiring the product rule. So the derivative dy dx of y prime is 1 times cosine inverse x plus cosine inverse is negative 1 over square root of 1 minus x squared. Cosine inverse is negative 1. So plus negative 1 over square root of 1 minus x squared. And then times f, which is x. So that part is done. Now we move to this minus. And this is simple, minus 1/2 1 minus x squared to the power of 1/2 minus 1, which is negative 1/2, times the derivative of the inside, negative 2x. And again, let me put an asterisk next to it. This is it. This is done as far as calculus. Now we are going to simplify. So first and foremost, this is cosine inverse. This is minus x over square root of 1 minus x squared. And this is negative. With this negative is positive. The 2 cancels out the 2. So we have plus x. In the numerator, this goes down, takes a positive 1/2 or a square root. So I hope you recognize this is. I hope you recognize this as a plus x over 1 minus x squared. So the final answer is dy dx equals cosine inverse of x.